Okay, so hello everyone. Welcome to the next episode of Warsaw Quantum Computing Group Meetups. It's already episode 78, so time flies. My name is Pavel. I will be the moderator today, and we have pleasure to host our great speaker, Michał Stęchły from PsiQuantum, for the second or third time? Third time, I think.
I think third
I
time,
think
yeah.
it's already third time with us. Which is great. And today Michał will give a talk about Construct, PsiQuantum software for FTQC research. Before we start, just a few announcements. So as you can see, this meeting is recorded, so the video will be later available on our YouTube channel, hopefully, if there are no technical issues, of course. And we've agreed with Michał that there will be some dedicated breaks during the talks when you can ask your questions, and there will be a dedicated Q&A session at the end, so you can keep your questions until the breaks or until the Q&A session, or you can also post your question on the chat, and we'll try to ask the question whenever it's suitable. We would like to thank our strategic partners for supporting us: Sonovero R&D, Quantum.io, Onyx, Cogit, AIQ Lab, and FinQubit, as well as our honorary partners who also help us advertise these meetups. Okay, so with this, I will stop sharing my slides. And Michał, first of all, thanks for being with us for the third time already. Thanks for accepting our invitation. As always, it's our pleasure to have you with us, and the Zoom is yours. So if you are ready, we can start.
Awesome. Thank you very much. First of all, thank you for having me. And wow, 78. Thanks for keeping, this initiative alive for all those years. I know it's a lot of hard work and a lot of initiatives are not surviving that long. So, great job, Pavel. Thank you for doing that. So, hello everyone. My name is Michał Stęchły, and I work as a quantum software engineer at PsiQuantum. And today I wanted to tell you about Construct. Before I get into Construct, I wanted to tell you a bit about PsiQuantum itself. Um, so, we are a quantum computing company based in Palo Alto, California. And our mission is to build and deploy the world's first useful quantum computer. And I will be focusing on the useful part today because I'm working on the applications team. Our role is to figure out how to, well, get good applications for quantum computers, how to make the quantum computer useful. And therefore, I will not be talking too much about the hardware or all the error correction architectures, but algorithms and applications. So first, um, I want to tell you that what we see on this picture, it's barium titanate, and this is one of the it's a material, and our components that we use in our photonic quantum computer, some of them are made with this particular material. The problem with this material is that it's not widely available. It's not something that's manufactured, on scale. But a couple of years ago, it turned out that if we want to build a fault-tolerant computer, we really need to make components out of BTO. So what happened is that a bunch of people at PsiQuantum sat down and figured out the whole manufacturing process for just this material. And I think we are now like leading producers of this material. And I'm talking about it because we are in the stage of development of quantum computing where there is a lot of breakthroughs that are needed in from hardware to kind of software and applications research. And in order to make our mission reality, really, a lot of these things need to happen. And another thing I wanted to tell you is about the scale of the endeavor that we are making. So if you are familiar with NISC, well, NISC devices are kind of relatively small. These are like single chips. And if we talk about fault-tolerant quantum computers, those single chips are just tiny parts of the whole device. So when I was part of DARPA quantum benchmarking program, kind of a couple of years ago, during one of the meetings, Josh Mutus from Rigetti said that they run math. And it turns out that in order to actually solve some of the problems that we were interested in that program, we would need to have a Costco-sized supercomputer, quantum computer, right? And for those who don't know, Costco is American store. It's kind of like IKEA size, but with groceries and plenty of other stuff. And that made us laugh. We thought, come on, this is like way too big. But actually, it turned out that if you actually do the math, that's correct. And here on this visualization, you see kind of the size, how big the first fault-tolerant quantum computers will be. And that's basically resembles more a supercomputer than kind of a regular computer or a chip. Next slide. Okay, and another thing which makes me personally pretty motivated for work is that, well, it's actually very quickly becoming reality. So on this picture, you can see a photo from a so-called groundbreaking ceremony in Chicago, where we are building one of our quantum computers. And that photo was taken, I think, in September last year. And here is another photo taken a couple of months later, where, well, we are starting to actually build a facility to house that, I mean, it's hard even to call it a device, right? That this huge quantum supercomputer that we've seen on the visualization a couple of moments ago. And we are not really doing that because we think that we will need it 10 or 20 years from now. The timelines are much, much closer. And while we at PsiQuantum don't have any public roadmaps regarding when our computer will be built, well, as you can see, we're already starting to build a facility to house it. I took a look at a couple of other companies and what their roadmaps say. So, Quantinuum says 2030, Alice and Bob says 2030, Pascal 2029, IBM 2029, right? That's not very far into the future. And it's actually just, a couple of years from now. And even if, as you probably should, you take some of those public announcements with a grain of salt, well, I think it is coming, and it's fault-tolerant quantum computers are much closer than we think. But the problem is that quantum hardware is kind of one part of the picture, and then we also need those useful practical applications, right? And there is a gap between these. There is a lot of work that we need to do on the side of the applications and algorithms to make sure they are ready for the first generation of quantum computers. And this, what we see here, is basically how our process for kind of working on new applications looked like a couple of years ago, when I think like 3 years ago when I joined PsiQuantum, most of the projects looked something like this. And it not just at PsiQuantum, actually in many other groups that I know of, it looked very similar. So first, you had to spend a couple of weeks on identifying what algorithm will be good for particular application, right? Then a couple of months went by to, well, write this algorithm in details because, sometimes you have a paper and in that paper they just say, here is a unitary which does something. But like how to actually make that unitary reality, that's a different story. That's the work that needs to be done. So that took a couple of months. Then you actually have to take those kind of big picture algorithms to compile them down to all the basic subroutines that you can use on a quantum computer. So, for example, like all the data loading, all the arithmetics, etc. And that also takes quite a bit of time. Then resource estimation. A couple of years ago, all the resource estimation were, maybe not all, but like a lot of them were being done by hand, and the software really just started to exist. So because there were no ready-to-go packages to do that, it was also taking some time. And then optimization of these numbers, right? You found bugs, you found, oh, actually you have a bottleneck here, but there is a more clever way to solve this problem, more clever way to implement this particular subroutine. It took another couple of months. So overall, a project like that was taking about a year, really, to go from, like end to end, from an idea to some implementation which we could resource estimate. And for those who don't know, what resource estimation is basically the process of taking an algorithm or application and estimating how much resources it will take to run it. So how many logical qubits we need, how many, well, particular types of gates, how long it will take to run it, given certain assumptions, maybe what's the energy consumption that's needed, etc. Fortunately, like the problem with, with this timescales is that going through this whole pipeline would take about, 9 months to a year. Since most of the work is being done, iteratively, you need to finish a project to think about it, get some feedback, and start another one. Then it doesn't really give us a lot of those cycles until 2030. But fortunately, we built out some tools internally, which allowed us to really speed up this whole process and collapse it from, something like a year to maybe a couple of weeks. And an example for that is where we did some work using algorithm, I think DFTHC, coming from this paper here. And basically the project started, I think, in April or May last year. And in September, we were able to produce this chart. And what it shows what's the active volume. It's like one of the resources we are tracking, right? And the number of qubits for different families, different applications. Each line is a different application, and it's calculated for different set of hyperparameters. We not only managed to, within a couple of months, to like implement it, but also optimize parts of the algorithm, find bugs in the original implementation and fix them. And generating this plot was taking about 5 hours at the beginning of the project, but then thanks to kind of all the optimization we made, getting this was at the end is taking about like 5 minutes. So my point here is that really the role of the tools in the research for fault-tolerant quantum algorithms is to kind of shorten the feedback loop, to like allow researchers, allow scientists to work faster, more efficiently, so that when they have an idea how to improve something, they don't need to wait for 5 hours to crunch the numbers and see whether there is an improvement, but they can click a button, go make themselves a coffee, get back, and actually see the results. And that's what we are trying to drive. And as much like as proud as we are of the results that we are able to get internally, I don't think any single group in the world can really tackle this challenge alone, right? We need to work together as a community. We need to come up with better methods, better ideas to make kind of useful quantum computers reality. Unfortunately, we are in such a phase of the development of the industry where rising tide raises all boats. And if some people in the community figure out a way to reduce the number of qubits needed by half for solving a particular problem, then all the other groups can, benefit from that new invention. And that's why our proposition to get faster to useful applications is using our platform Construct. So Construct is a platform developed at PsiQuantum that we use internally. We have been using for years to develop fault-tolerant quantum applications, and now we are sharing that openly with the world. It is designed for fault-tolerant algorithms. It has absolutely nothing to do with any NISQ algorithms, and there is a couple of reasons for that. So, a lot of the NISQ applications are designed for hundreds, maybe thousands of operations, while in the FTQC you easily can get into billions. I would say that the kind of abstraction hierarchy in NISQ is relatively shallow, while the one that you have in FTQC is many, many, many layers more complex. So it's just even just the algorithms, right? They span like several layers. We don't really focus on any issues with the error mitigation or just like thinking about errors. We work on the logical layer, and our focus is more on making sure we use the least resources. And also, just the scale of the fault-tolerant devices allows us to work on more meaningful, more impactful applications. So Construct consists of many different tools. So we can group them in like two main groups. So one is PsiQDK, PsiQuantum's development kit, which in turn has a bunch of different Python libraries inside. So everything here is something you can basically pip install. So you can go to pip install PsiQDK and just have access to all of these. But it also has some visualization tools, such as Circuit Designer or Research Analyzer that I will also be showing today, which are more convenient to use online. You can access all of this on the construct.psiquantum.com. And our timeline is that we opened access to Construct, PsiQDK, katas. I will talk about katas later. 2 weeks ago. Later this year, we plan to release Workbench Applications, which is our library of full application, like software for like running those end-to-end applications, and also algorithms textbook, which will be basically educational materials about FTQC algorithms. And I'm saying, the PsiQDK is open access because you can pip install it, but unfortunately it's not open source yet. Well, we didn't want to wait with sharing that with the community, and so we decided to go with open access first, and we're working hard to open source it like at some point later, I hope later this year, but no promises yet. And that's enough introduction. I would like to proceed to actually showing you how to use PsiQDK, what are the capabilities. And probably if anyone has any questions from what I said, I think this is maybe a good moment to ask them.
Okay, let's see if we have some questions. I do not see any questions
Nothing
on
in
the
chat.
chat, but maybe someone would like to unmute and ask.
Also great. So
Okay, we
let me
can proceed.
proceed
Mhm.
and show you what demo I prepared for you. Um, eh, okay, first, is this size of the font enough, or maybe let's like that? It's good?
Yeah, I think it's okay.
Awesome. So, up. Okay, so we'll start from just running these kind of boring imports that we'll use throughout the yes, this is Python only software stack. Yes. Part of the stack is in simulator, for example, is in C++, but all the kind of API is in Python. So the first thing I wanted to show you is Circuit Designer. And there is this particular paper encoding electronic spectra in quantum circuits with linear T complexity, which contains or like describes this really nice algorithm which is called alias sampling. And alias sampling is basically one of the ways to load some data onto a quantum computer efficiently. Basically, its goal is to prepare this like L state, which contains some data that we wanted to load. And it looks like this, right? So basically, this is it consists of a couple of different subroutines. There is uniform state preparation, also called USP. This is kind of a data loader. This is like a comparator, a swap, some Hadamard's. That's how it looks like. And something that is, I think this is one of the first visualization tools that we have developed in our team. This is Circuit Designer. And this is something that really helped a lot the researchers in our team to work with circuits, to design algorithms. And because, as you will see, it's basically a visual interface to build those circuits, but not just gates, but actually much more complex and complicated algorithms. So here I will quickly just show you how you can kind of re-implement this picture here. So it's figure 11. This is 12. Okay, it's here, right? So let me just kind of get it down there so I have it for reference. And okay. No. So okay, so what do we have is we need 5 registers. So we have add registers is command 1. So I will just create 5 registers here. And they are called cat. Oh, I already have it from my previous attempt. So one is called like this. This one is called like that. And the third one is just 0 state. So that's fine. Okay, so we got the registers. Now I would like to add some routines. It's well, okay. So to keep the layout nice, actually I will first add a column And then inside this column, I will add those two routines. Why it got inside? Oh, now it's good. And they're called uniform L and H to the power of O times mu. Then we add another column and we add 3 subroutines into this column. Okay, so 1, 2, up, 2 column, sorry. Okay, there is a better way to do that actually than drag and dropping, sorry. So we have column here, and I can use this bar on the right to put stuff into the column. And no, did I work? Oh, now it works, sorry. Up and hop. Okay, now they are all on the same rail, so I will keep them on rail 1. Another is on rail 3, and yet another on rail 4. Now they are controlled on this in L, so I will just say that the control rail is 1. Okay, and I will change the name of this. Oh, this is target rail. I wanted to change the label. Oh. In L. Okay. Okay. Alt L, etc. So I don't want to bore you, with all of that, but as you can see, we are already halfway through. And here is, you can see I prepared earlier this whole circuit. It's not in any way executable. It's not in any way ready for simulation, but just being able to, draw the circuits without drag and dropping pictures in Lucid or whatever other people are using is something that like our researchers really love. And you can find some, this is pretty simple example. But here you can see that really the cool part of this is that you can make each of these items like fully collapsible, and you can, however you want, zoom in and out in the algorithm to look at it at like different layers. And while alias sampling is a nice example, really this is those really much bigger algorithms like double factors, like DFTHC, right, is where you can, there is like a lot of information. And one static image of this is my circuit doesn't really do justice to kind of the complexity that we have here. And yeah, as you can see, really nice visualization tool and really, really useful. You can check it out on the Construct website and just kind of start playing with that. For even if you don't use any other part of our stack, I think just this one thing is already worth knowing about. Okay, so that's Circuit Designer, but actually something I spend most of my time working on is Workbench. Before I get into Workbench, I see some questions. So I will answer them. So first, from Krishna Gupta, can it simulate continuous variable QEC codes? No, this tool has nothing to do with error correction. It's not a tool, like nothing I'm showing today are tools for working with error correction. They are all tools working on like a logical layer, right? So we assume there is some error correction underneath, and we don't really bother knowing what that error correction kind of can be. It's just like abstract logical circuits. FT algorithms will run for hours, days, week. Is this feasible in a language which is not compiled and may raise a runtime error? So actually, first, I think something that makes Workbench stand out is that we design it to actually be our kind of access point to our quantum computer. So basically, Workbench is a framework that we will use to run programs on our quantum computer, and it's not just for like simulation or just for resource estimation. It actually produces executable programs. Once we have hardware, we don't have hardware yet. So, I mean, it could raise a runtime error in the middle of your computation. Yes. At the same time, I think if it's robust enough, then if that doesn't happen, we really are testing to make sure it is ready for the prime time. Does it work using photonic gates, or it's a universal tool? It is absolutely a universal tool. It doesn't make really any assumptions about the underlying hardware or architecture. As I said, abstract logical circuits. Actually, the feedback that I sometimes get when talking about it is like people would actually like it to be more specialized and would like to be able to reason more about photonics with the software, but this is not what it is for, right? It's a general purpose quantum algorithms development toolkit. There is one caveat, but I will get to that later when it's time. Okay, so how do we work with Workbench? Workbench is part of the PsiQDK. Right now, the kind of two main libraries that we have is Workbench and Workbench Algorithms, where Workbench is the core engine for running it all, and Algorithms is kind of a library of all the algorithms that we have implemented. So first, we create this QPU object, which we use for kind of basically handling all the simulation, calculation, resource estimation, and whatnot. We create two qubit registers. So one we call target, another we call control. And as you can see, we create target with 3 qubits, control with 2 qubits. Our number of qubits is 5, so that's good. If, for example, we tried to allocate more qubits than we have, then we are getting a runtime error because our QPU doesn't have enough qubits. And then we basically apply an X gate on a target register with that's being control on the control register. So as you can see, it's like 2 control, 3 target kind of X gate. There is this QPU.draw method, which allows us to draw a nice picture diagram of the circuit. As you can guess, there is many different gates here. I won't kind of be showing you all of them because that's kind of not the point. But there is some nice syntax that allows you to do, for example, things like this. I want to take first qubit from the first register, second from the second, and kind of apply that. Or work on ranges of registers, right? We see that we from 0 to 2, so that there are 2 of them, etc. So that's kind of how the syntax looks like. And a really important part of Workbench is the kind of compilation engine, right? The compilation passes. So if we draw a circuit that looks like this, again, it's like nothing particularly complicated. As you can see, we just defined a register of size 4, and we apply first y, like our y gate with like some angle on the first qubit, and then for the other qubits, we apply the controlled versions. This particular circuit prepares a W state, which kind of looks like this. So we have, the same probability of getting different states with like power of 2 indices. And the circuit looks like that. It is what it is, right? But why the circuit is, why we are looking at the circuit is because it is a good example to show how we use compilation passes in Workbench. So compilation passes are, basically ways to transform some gates into other gates, or like even more generally, I shouldn't be talking about gates here. It's like operations. They don't need to be gates. So some operations into other operations. So for example, the fault-tolerant device will most likely not have access to multi-controlled operations. All the multi-controlled operations will need to be compiled to single controlled operations. Okay. Sorry, my bad. One or two controlled, basically. This is fine. So, okay. What we do here is we decompose those kind of multi-controls into what we call kind of clean ladders. And as you can see, we get a circuit like that, which is equivalent to the previous one, but well, like problematic multi-controlled rotation gates have been translated to those elbows, which these elbows are basically operations that are like kind of AND gates. And they have been defined by Craig Gidney in kind of one of his papers. We call them Gidney elbows. So then, as you can see, so there are like left elbows and right elbows. And as it turns out, if you put left elbow next to right elbow, they cancel each other. So we can make a use and optimize this circuit to, for example, get rid of this particular pair here, adding an elbow reduction filter, right? So now we have, again, a different circuit that's slightly more optimized. Then, well, rotation gates, controlled rotation gates are slightly problematic. We actually cannot implement them directly. What we want to do is we want to decompose them into a set of kind of CNOTs and 1 qubit gates. So we can do that with this another filter called like single control filter. And as you can see, each of the controlled rotation gates, one controlled rotation gate got divided into two rotations, two rotations with like different angles. And well, then there is like yet another filter that allows you to decompose those kind of Toffoli gates, basically, so those like elbows, into something that's more directly implementable in hardware. And as you can see, this kind of compilation pipeline took us from this relatively simple picture to this slightly more complicated picture in a bunch of steps. But this is where a lot of the optimization comes in, and a lot of the resource saving when working with those fault-tolerant algorithms. We could also do Ross-Salinger filter, as we have that. Someone unmuted themselves. There is some noise, so if you could mute yourself, or Pavel, if you could, thank you. But I didn't run Ross-Salinger filter on top of everything else because taking one rotation gate with the angle that's kind of not simple multiple of 90 degrees looks like this, and it would just like wouldn't fit this picture nicely. Okay, so this is some basic syntax of Workbench, some basic filters. Now I will show you how we use Workbench to actually implement, again, some useful algorithms. We are, again, using the same paper. And this paper proposes, defines maybe a circuit that's used for basically loading the data. And what it basically does is, okay, if it's controlled, so like if control is true, then it loads a particular operation xi depending on what's stored in this register L. Okay, so if register L is like all zeros, then it will load x0. If it's kind of 1, then it will load x1, etc. So if we look at it and like try to describe it using like classical Python code, we would say if control equals 1, then our output state psi, so right this state, right, is basically load the data given by index L. Obviously, if we do that using quantum computer, we can load all the data coherently in superposition, so it gives us some extra power. But let's see how to implement this particular operation, which is really, like basically in, I think, every single algorithm for FTQC that I've seen. So first, again, we instantiate our QPU object. We define our registers. And we're not using qubits objects this time. We are using q, uint, and qint. So we have those. We're not working just on qubits registers. We actually want to make sure that we can handle integers, unsigned, signed. There are like other types as well. And this is useful because in those cases, if we want to load some data that's some's positive, some negative, then Workbench takes care of encoding that properly for us. Then we write 1 to control because, hey, like we want the control to be set to 1. And we want to set like the index to 7. So this is index register, right? It's this guy here. And we want to set it to the value 7. So basically we want to load x7. And it turns out that this is like -1 here. So what we do in order to do that, well, we just like do an X gate, which flips all the qubits kind of given by this mask of 7. And then for each item in the data, we apply this operation, which basically says, okay, so load the data like D on the qubits if this condition is met. And the condition is that the index is I and the control is true. Right? So for the first one, if our index in the data, if the index register is equal to I, we know it's not because we just set it to 7 and it's not 0. So we will know this will fail. And we know that this particular operation will, in our case, just evaluate to nothing. But iteratively, we go like that. And then we get this particular picture where we load all those 8 pieces of data that we had in this list into our quantum register. So there is a couple of issues actually with this circuit. It's a nice high-level abstract thing. But as I mentioned before, one of the issues is that we are not really able to handle multi-controlled gates on FTQC. We want to compile it down to some other operations. So if we look at the figure 5, we see that what they did in that paper is that implemented something like that. So in order to do this, we can add some filters. So I will add a filter, and this is a filter that I already mentioned. Filters, sorry. Right, so this is it. And basically this picture, it looks a bit different, but conceptually, this is exactly the same as what they proposed in the paper. The second problem is that, as I mentioned before, some of those elbows will cancel each other out. So, this circuit contains way too many gates than it really needs to. So we need to get rid of that as well. And as we've seen before, there is this elbow reduction filter, which we can add to the pipeline. And Oh, and actually nothing happened. So basically this picture is kind of, again, doesn't really resemble this one, right? It's much more like this. And the reason for that is that if you go and read the paper carefully, you will see that they are using different kind of endian than we use here. And it is somewhat problematic, but fortunately, because in Workbench we can, have some nice syntactic sugar, which allows us to treat the whole registers as kind of entities, and not kind of just separate qubits. We can just revert the whole index register. And if we do that, we get this picture, which, as you can see, is much more similar to this guy here. So we achieved our goal. So I will ask if there are any questions or comments, and drink some water while you are typing in the chat or unmuting yourself.
Okay, thanks, Michał. I see some questions on the chat. Perhaps you've already answered some of them during
Yeah, I
your
already
talk.
took all of
Yes,
them.
all of them. All right, so
Yeah.
let's see. Do we have more questions? Maybe someone would like to unmute.
Okay. If not,
Okay,
I'll
you can
proceed.
proceed.
So, all of this is nice, but as I mentioned, like working with gates is cumbersome. I in the past have written the whole blog post about why I think circuits are not the good abstraction. I've co-authored a paper where I argue why circuits are not a good abstraction for working with this. But so far, we've seen kind of only circuits. But fortunately, we can pack in Workbench. We have like an extra, abstraction for the subroutines, which are called kubrics. So let's say we want to load two sets of data and then add the numbers coming from, like add those data sets together. It would be nice not to have to write all these kind of bespoke circuits and have some modularization. And this is where kubrics come on the stage. So again, we create some QPU, we create the necessary registers. So we have two index registers, two target registers, and then we have two different sets of data. And then we create this select kubric, right? So this algorithm here that is described in the figure 3 of the paper is called select because it's one of the many implementations of select, right? Because it's select because it like basically selects a piece of data from a table. We call this binary tree select, and we kind of want to compute the first and the second one. So the first one loads the data one on those registers. The second one loads data two on these two registers. And then we want to add whatever is in the target registers, right? So we take a Gidney adder. Again, there are many different adders. In this case, we are using the one proposed by kind of Gidney. And let's take a look what we get. We did drawing with this like show kubric so we can see the structure a bit better. And if, okay, I don't want to zoom out like this. So what you can see is that we have this binary tree select, right? And this one is working on the register like index one and target one. It's using some ancilla qubits, but it's not really touching anything in the index two and target two. Similarly here, it's working on two different sets of registers. And then here we have an adder. So whatever we get in this kind of target one and target two registers is now the result of adding the data coming from these two lists. And yeah, this type of arithmetic operations is something that's used in a lot of the different algorithms. So being able to do that is pretty useful. So now I wanted to show you something that I personally work most on, which is resource estimation. And let's take a look at the alias sampling algorithm again. So we like to use this particular algorithm because it's not so complicated that you will get lost in, all its structure, as you definitely would if we were talking about kind of this monstrosity here, right? But at the same time, it's complicated enough that it has some structure. You can analyze some interesting behaviors here. Okay, so what we do here is, and I will not be going through that step by step, but basically we instantiate kind of the algorithm that's described in this picture, using a couple of different kubrics, right? So for each of the subroutines here, we have a different kubric. This is USP, this is data lookup clean, this is comparator, swap up. So, we have a bunch of these. And what we can do is using the resource estimator interface, we can, okay, I'll actually draw the circuit just so that you QPU.draw. You see how it looks like, right? So this is the circuit that we are talking about. So what we can do is we can analyze how many different types of resources are used for this particular algorithm. So we see that there is that many left elbows, right elbows, rotations, T-gates, Toffoli's, and what's the number of qubits that's needed. We actually, as you can see, we are using this high water thing because throughout the compilation process, some registers might be allocated and deallocated. So our workbench is like keeping track of all the allocations, deallocations, and making sure that if some qubits are clean, we can reuse them for something else, and therefore not waste the resources. Okay, so we have some information. We know what kind of resources are used. And actually, the resource that a lot of the papers is tracking is, for example, like T-gates or Toffoli gates. In our case, we actually have this resource called active volume. And this is this one place that I mentioned before where we are making certain assumptions about the architecture of the fault-tolerant computer we will be running on. And we are assuming, well, the architectures that we proposed, the active volume architecture. And if anyone is interested in learning more about that, I can link to a paper later. But I would say, without getting into kind of too much detail, that let's just like treat it as yet another resources. This one is actually a bit specific for our architecture, our hardware, but basically everything else that I was showing is totally hardware agnostic. This is also not really hardware, it's more about the architecture and like how you connect different modules in your quantum computer. It can be implemented with like other architectures than photonics in principle. But it's particularly well suited for photonics. So active volume is this number. It's like a single number because you can see we have elbows, relbows, like different types of gates that maybe we need to kind of look at and analyze differently. Active volume is fortunately a single number. So what we can do is we can actually take a look at yet another tool that we have in Construct, which is the resource analyzer. And if we take our QPU object and export it into this kind of resource analyzer data format, we can draw a call graph or a flame graph if you prefer that. and see which subroutine takes how many resources of particular type. So as I said, let's focus on active volume. And okay, we see that the biggest offenders are compare greater equal, right? So comparator and the data lookup clean. Okay, that's kind of good to know that probably if we want to optimize our algorithm, we need to focus on these two subroutines. But then maybe we would like to think, but maybe that's true only for a particular size of the problem, right? So if we don't take 4 inputs, but let's say 20 inputs, well, we get different numbers, obviously. All the circuits get a bit more gnarly. But now if we analyze the resources, we can see that, oh, actually the bottleneck is in a very different place. Now it's USP that's taking most of the resources. And this is, really useful to perform this type of resource analysis and like trying to find what are the places in the algorithms that you want to analyze, you want to optimize. And alias sampling is relatively small example. We have it here as well, but some bigger and more kind of practical ones is this one for like DFTHC block encoding, where alias sampling is just like one little box inside this whole picture, and this tool really allows you to debug, find patterns, and analyze as I said, analyze the algorithm much faster than if you try to do it by hand or by analyzing the code. A side note, if you decide to give it a try and play with it, while those widgets in the Jupyter notebooks are really nice and helpful for small for like quick debugging, sometimes when the amount of data, so the size of the circuit is bigger, then it's better to export it to a file and load onto the web version because it's just can handle kind of more than what you can do in notebooks. So just, okay, I just like showing something because I think this is where things start getting ridiculous with the type of the applications we work on. So if you try to look at this picture, this circuit is still kind of, it's complicated, but you still can reason about it. But often we are not loading 10 or 20 pieces of data, but we're loading like 10,000. We are trying to do simulation. That's will be too much. Damn, I didn't try it ahead of time. Yes, maybe I did something wrong with the number of qubits. Live demos. No, this is something else. Damn, sorry. I wanted to show a bigger one, but I think I have something wrong in this that it doesn't allow me to. Okay, one last try. If it's resource, nah. Sorry. I just wanted to show a bigger circuit, but as you can see, something is. I need to. I must have a bug somewhere here. Okay. Anyway, so this is about resource estimation, and okay. Sorry. Now I broke it because I have too much. So let's just run the smaller one. And now it should be good. Okay, yeah. So we can also export to the circuit designer, and basically, rather than play with this static representation that we see here, we can analyze this whole circuit as kind of using circuit designer and kind of those collapsible interface, which is super useful. Okay, so before I get to the kind of extra material and I'm getting to an end, um, I wanted to actually show, because I was playing around, like was wondering what would be a kind of another case to show how maybe this would be, what would be an interesting place to show how these tools are useful. And I decided that maybe let's try running those QREs with different filters and see how using different filters will influence the resources that we have. And basically, I have two implementations of alias sampling here. The only difference is that in the first one, we run QPU without any filters. And in the other one, we run it with these particular filters. And actually, the resource estimation part runs some filters under the hood. But we can see if we look at the active volume number, we can see that we are getting 1959 here and 2017 here. So clearly, if we run those filters, we do some decomposition, the resources are higher. So that's kind of not good. And in order to actually kind of take a look at this and compare it, we can just open two of these and go one by one and see which subroutine is the offending one and which is causing the jump in the resources. So we see that in the first one, we got 206, 50, 939, 272. And here we have the same number, except for USP, right? So we can see that there is something going on in the USP that, well, makes one implementation less efficient than the other. And if we kind of draw the circuits, now making use of resource analyzer, we know what we want to focus on. We want to focus on USP. And we see that what happened here is this USP is just kind of a bunch of Hadamars. And this guy here, and as I mentioned, unfortunately, for bigger ones, it doesn't display so well. So I would have to export it. But basically, we also have this. And this is basically a decomposition of controlled Hadamard. So if you want to implement controlled Hadamard using Clifford gates, this is what you get. And if you spend enough time looking at it and thinking and wondering where the discrepancy comes from, it turns out that active volume operations can be kind of internally optimized. And because we are using here the gates without any compilation, we are using under the hood the active volume value for controlled Hadamard that's optimized using ZX calculus. While in here, we are explicitly kind of expanding it to gates, and therefore we're not taking making use of this optimized ZX calculations. So the active volume is like slightly higher if we compile out everything explicitly. So, this is, I would say, pretty technical detail, but at the same time, you can imagine all different families of bugs and issues that you can run into that kind of having this type of tools helps with navigating through and debugging. Okay, and last but not least, if you would like to learn more about Construct, I will be sharing all those links in the chat. But basically, we have Kubrick's library. Oh, that's unfortunate. Forbidden. Wow. Okay, sorry, I wouldn't navigate to the link. Kind of nice. Okay, so it's here. Ha! Wonderful. I got some, I think, oh, our servers just broke. Amazing. I have no clue what happened, but apparently
Oh, Murphy's Law.
Murphy's Law. It's like, but the whole, as you can see, like the whole documentation site just died the moment I was making presentation. Like, who would have guessed? But what I want, what I wanted to say is that Kubrick's library is this library of all the subroutines we have implemented. So if you want to see what we have, this is the place. It's in the yeah, I can show you. But if you go to the docs, PsiQDK algorithms, then you can find it there. And the other thing actually, fortunately, will work. So if we go to the PsiQDK, and I have this link here, Workbench katas. So this repo is a repository of quantum katas, and this is a collection of kind of tutorials and kind of problems prepared by my wonderful colleague Maria Mikhailova. That's Maria. Uh, she used to work at Microsoft, and maybe you know her quantum katas in Q Sharp. She has rewritten all of them into PsiQDK, and I would say this is like amazing resource to just learn about all different types of like fault-tolerant algorithms. As you can see, there is, some classics like Grover, Deutsch, Josa. Uh, there are like some others, like I mean QPE, short. These are all like pretty textbook. I think there are like some variants if you start digging into those notebooks about some kind of or like solving SAT with Grover's algorithm, like slightly more complicated. And yeah, this is a great place to kind of learn more about the algorithms. And so library katas and a newsletter, together with my friend Conrad, we are writing a weekly newsletter about, well, writing software for quantum computers. And it's aimed at both software engineers and researchers working with code. So if you would like to see what our opinion is or learn something from us, this is a great place to do that. And well, I wanted to finish this on the Construct website. Oh, it works now? Huh. You see, it works now. Amazing. So sorry, I'll just get back to the Kubrick's library. So here there is Kubrick's library. So these are all the subroutines that are implemented. Feel free to kind of explore it. And yeah, that's everything I had to show for today. So thank you very much. And if there are any questions, I will be happy to take them.
Great, thank you. Fantastic. Thanks, Michał. All right, it seems that you've already answered the questions that our participants had on the chat, but maybe there are some other questions. Maybe someone would like to unmute and ask. Let's give some time.
Don't be shy. I mean, if you have questions which are, I would say, not directly connected to the presentation, that's also fine. If
Okay,
not,
yes, I think we can conclude then. Or maybe
okay.
Michał, you would like to add something.
Let me actually just share the links in the chat.
Mhm.
So it's easier to, I forgot to do that immediately. Um,
Oh, there is a
oh,
question actually. There are
okay,
some
great. I will
questions.
read it in a moment. Um, oh, just pasting links. What I wanted to say is, yeah, if you come up with any questions later, easy to find in the internet. My email, I'm also pasting it in the chat, so feel free to reach out to me. And I'm reading the question. I've been looking at PsiQDK Workbench and noticed that Workbench exposes Q TensorNet. Yes. I'm interested in tensor network contraction engines and wanted to understand where help would be actually useful. Is the current TensorNet path meant mainly as Q-to-Q wrapper, or is PsiQuantum considering a more configurable TN simulation surface in a workbench? For example, okay, I will not read all the details as I don't even understand these tensor network words. Okay, so if I wanted to contribute constructively, would a GitHub discussion issue around first-class TensorNet configuration and benchmarks for workbench be useful? So I would say that first, yes, we have integration with Q2Q, and it works pretty well from what I heard. I haven't used it myself, but like my colleagues work on that. I cannot really comment on the details of it, so I would first check out the kind of whatever is in documentation. I hope is helpful. As per contributions, since it's not, the code is not open source, it's a bit hard to see exactly what's happening under the hood. But I think the best way would be to either create an issue or discussion on GitHub. We are, monitoring that. And um, probably then we'll connect you with one of the engineers who worked specifically on the Q2Q integration, and then they will be kind of best equipped to see if there is any way to contribute or what's the best way to benchmark. We obviously have some scripts internally for benchmarking, so maybe we could share some of them to help you do some research on the topic. I think starting an issue, like creating an issue or discussion is the best, currently the best way to go. I hope that answers the question, but Dennis, if you have any follow-up, feel free. No follow-ups, I understand. Okay, cool. Any other questions?
Okay, last chance to ask now, or actually almost last chance because I will also share my slides once again just to announce the next meetup. So you will have one more chance to ask a question. Hope you can see my slides now. All right, so here are just some links if you are interested. So the video will be later available on our YouTube channel, so you can join our social media groups, follow our pages, follow our YouTube channel, join our Discord server, subscribe to our newsletter. We thank our strategic partners once again, so Novero R&D, Quantum.io, Onyx, Cogit, QLab, and FinQubit, and we thank our honorary partners as well. If you like our activities, you can donate, especially if you are in Poland, you can donate 1.5% of your tax. And we invite you to the next episode, episode 79. This time it will be on Saturday. Um, so it's an exception because our next speaker, Jacob Cybulski, lives in Australia. So there is a huge time difference. So instead of hosting our meeting on Thursday evening, Polish time, we decided to organize it on Saturday at 11 a.m. in Poland. So I hope you can join. I know that for our participants from the US or Canada, it can be more challenging, but maybe you'll manage, hopefully. If not, then we are also going to record it. So the exact title is not specified yet, but we'll announce it in about 2 weeks from now. So stay tuned, and as I said, feel free to join our groups and follow our profiles to stay up to date with all our activities. Okay, I will now stop sharing my slides.
Thank you. So
Maybe last
Go back.
questions to Michał
yeah.
Can you go back to the first set of links where you stop?
Yes.
with the links.
Yeah, the first slide that had all the links.
All right.
I just want to take a shot and I'll go from there.
Okay.
Yeah, there you
Yeah.
go. Hold on.
All these links are also
Cue.
on our website, on the website of the Quantum AI Foundation. There is subpage titled, it's named Contact, and there you can also find all the links.
Okay, thank you.
Thanks.
So I also wanted to just answer the question from Krishna. It's like you said, we assume that it already has QEC done. What was assumption, like surface codes? So I mean, basically, I don't care what kind of error correction would have been done because we just assume we have logical qubits and logical operations, and you can take a program written in Workbench and interface it with either our quantum computer, which will support certain QEC protocols. I'm not sure exactly which ones because I'm not QEC expert. Or you can, but as I said, I think it's like active volume stuff, so it's slightly different than surface codes. But then you could equally well take the program written in Workbench and Workbench basically just like emits operations, right? So it says like, I want to do X gate here, I want to do kind of C node here, I want to do T gate there, etc. And that's kind of the output of Workbench is like an op stream. So you can stream that op stream into any interface that you have for any QEC kind of backend, and it can consume those ops and then like perform all the all the error corrections on those ops. I mean, obviously, you probably want to modify it and like run through different compilation passes depending on what's kind of the target set of operations that are supported on particular hardware and so on. But in principle, it's agnostic of the what QEC is being done. We are not running any QEC in PsiQDK, right? So
Mhm.
I hope
Okay.
that answers. Yeah. Okay.
Okay.
Thank you very much.
I'll now stop recording.